At 0306 this morning, half the planet went silent. Not slowly, not gradually, all at once. Pilots mid-flight reached for their radios and heard nothing. Ships at sea lost contact with the shore, and the official forecast written just hours before, it said the sun was quiet. It wasn't. What followed was a coronal mass ejection travelling at nearly 2,000 kilometers per second, 4 times average speed, aimed at a planet carrying 11,800 satellites, 8 days of invisible radiation damage already baked into every circuit in orbit, and 4 astronauts 43 hours from leaving Earth's only shield. Stay with me tonight, because the flare was just the opening act, and you'll want to stick around to know what's coming next. If this has you hooked and you genuinely enjoy these nightly updates, subscribe to the Sky Lab, and tell me what you think. After everything that's been happening here on Earth, is this mass ejection the sun's way of asking whether we are paying attention, or what exactly is this? Let's get into it. Part 1. The blackout was real. At 0306 Coordinated Universal Time this morning, half the planet went silent. Not metaphorically silent, not the internet was slow, silent. High-frequency radio, the backbone of aviation communication, maritime navigation, military coordination, and emergency response across the entire sunlit side of Earth dropped out simultaneously. Pilots mid-flight couldn't reach air traffic control. Ships at sea lost their primary communication channel, and the people whose entire job is to watch the sun and warn us when something like this is coming. They were catching up to something that had already happened. The National Oceanic and Atmospheric Administration classified this as an R2 radio blackout. Now, I want to stop right there because the word blackout sounds like something a tabloid writer invented to sell clicks. It isn't. R2 is official NOAA space weather scale terminology. It means high-frequency radio propagation has been severely degraded across the sunlit hemisphere. It's the kind of language government agencies use precisely because it isn't dramatic, it's accurate. When NOAA says blackout, they mean blackout. Here's what actually happened at the physics level, because it matters for everything that comes next. The sun released a surge of X-ray radiation. That radiation, travelling at the speed of light, reached Earth in approximately 8 minutes. When it hit the upper atmosphere, it slammed into a layer called the D layer of the ionosphere, a region roughly 50 to 90 kilometers above your head that normally helps bounce high-frequency radio signals around the curve of the Earth. The X-rays ionized that layer so aggressively that instead of bouncing signals, it absorbed them, like trying to shine a flashlight through a wall of black foam. The signals went in and didn't come out. Every pilot, every navigator, every operator who depended on that communication layer experienced the same thing at the same moment: static, then nothing. The flare itself was classified as M5 class. On the solar flare scale, M class sits in the middle, above C class routine flares, below X class major events, and M5 is significant. It warrants monitoring. Under most circumstances, it would be the main story. But here's the thing, and this is where this event takes a turn that most coverage hasn't properly addressed. The flare is not actually the main concern today. The flare was the muzzle flash. What we're watching now is the bullet. At 0300 Coordinated Universal Time, 6 minutes before the blackout hit, radio telescopes detected what's called a Type 2 radio emission. That specific signature means one thing: a shockwave is moving through the solar corona. And shockwaves in the corona mean one thing: a coronal mass ejection has been launched. Not inferred, not predicted, launched, already moving. The question isn't whether a coronal mass ejection happened. It did. The question is where it's going and how fast. The velocity reading on this coronal mass ejection is 1,872 kilometers per second. Let that sit for a second. The average coronal mass ejection travels somewhere between 400 and 500 kilometers per second. This one is moving at roughly 4 times that speed. To put it another way, if this thing is aimed at Earth, the margin between "we knew it was coming" and "it's already here" is measured in hours, not days. And here's the part that should make every space weather forecaster deeply uncomfortable. The official NOAA forecast issued at 0030 Coordinated Universal Time, just 2.5 hours before the flare, described a quiet sun. Quiet. The system specifically designed to monitor our star and give us advance warning was, at the moment of this eruption, telling operators to expect nothing unusual. Detection lag versus real-time solar behavior. It's not a scandal, it's a limitation. But it's a limitation with consequences, because right now, with a coronal mass ejection moving at 1,872 kilometers per second toward an unknown destination, the difference between we saw it coming and we're already inside it could determine whether the next 48 hours are merely complicated or catastrophic. We don't yet know where this coronal mass ejection is headed. That's not a rhetorical device. It is the central, unresolved fact of this event. And everything else we're about to discuss, every satellite, every orbital system, every human being scheduled to leave Earth's magnetic protection in the next 43 hours, sits downstream of that one unknown. Part 2, the anomaly no one is explaining. Something else is strange about this event, and almost no one is talking about it. If you go into the NASA Space Weather Database of notifications, knowledge and information, which researchers just call Donkey, because apparently government scientists enjoy acronyms, and you look up the source designation for the flare that triggered this morning's blackout, you find 2 letters. NA, not applicable, unknown. For an M5 class solar flare producing an R2 radio blackout and a coronal mass ejection, travelling at nearly 2,000 kilometers per second, the origin point on the Sun's surface is officially listed as unidentified. That is unusual. Genuinely unusual. Flares of this magnitude are almost always traceable. The Sun's surface is covered in active regions, areas where intense magnetic field lines break through the photosphere, tangle, and occasionally snap in explosive reconnection events. We track these regions continuously. We give them numbers. We watch them rotate across the solar disk. An M5 flare normally has a clear address, so why doesn't this one? The 2 candidate regions that analysts are currently looking at are both sitting near what's called the solar limb, the extreme edge of the Sun as seen from Earth. Region 4397 is positioned at approximately north 15 degrees, west 95 degrees. Region 4398 is at south 16 degrees, west 97 degrees. If those coordinates mean nothing to you, here's what they mean practically. Both regions are sitting right at the edge of what we can clearly see, which is the worst possible location for determining the magnetic complexity of a source region, and crucially, for modelling the trajectory of anything launched from it. This is where the limb positioning problem becomes critical, and it connects directly back to the question we're trying to answer. If the source region is genuinely at the western limb, that's actually somewhat reassuring for Earth. A coronal mass ejection launched from the far western limb tends to be directed away from us, angled into interplanetary space in a direction that won't intersect our orbit for another several days, if at all. But if the NA designation reflects something more ambiguous, an emerging active region that wasn't yet catalogued, or worse, a behind-the-limb eruption whose shockwave was energetic enough to produce a flare signature visible from Earth without the source itself being on the visible disk, then the trajectory calculation changes completely. There's also a third possibility that no one wants to say out loud in official briefings, but that the data doesn't rule out. The Type 2 radio emission that preceded the flare detection timeline isn't just a signature of a coronal mass ejection, it's a signature of a fast-moving shock propagating outward. In some complex eruption events, the coronal mass ejection actually launches before the associated flare peaks, meaning the ejection was already underway when we first detected the X-ray spike. If that's what happened here, we've been watching the afterglow while the main event was already in transit. The instrument we're counting on to sort all of this out is the Stereo-A spacecraft, the Solar Terrestrial Relations Observatory, which sits roughly ahead of Earth in its orbit and gives us a side-angle view of the Sun's corona that SOHO and ground-based observatories can't provide. Stereo-A's coronagraph data should, in theory, show us the shape and direction of the coronal mass ejection structure. But there's a time delay in processing that data, and there's a dependency on data transmission windows, and while we're waiting for that resolution, the coronal mass ejection isn't waiting with us. Here's what the lack of source identification actually means for the central question. Trajectory modelling for coronal mass ejections depends on knowing where on the solar surface the eruption originated, what the magnetic field geometry looked like at that source, and what the surrounding solar wind environment looks like in the direction of propagation. Strip out the source identification, and you're running a model with a hole in the most fundamental input field. The uncertainty doesn't just expand, it multiplies. And every hour that the coronal mass ejection spends in transit is an hour during which we either narrow that uncertainty with new data or arrive at impact still guessing. What we know for certain is this: something significant erupted. It launched a fast coronal mass ejection, and the origin point is still not confirmed, which means the most important fact about the most important unknown in this story, where is this thing going, remains, as of right now, officially undetermined. Part 3. The classification problem. There is a discrepancy in this event that most coverage has either missed or quietly walked past, and it's worth spending some time on because it changes how we should think about the coronal mass ejection that's now in transit. The flare is classified as M5, that's the official GOES satellite measurement, fine. But NOAA's space weather scale shows this event producing R3 impacts, classified as strong on a 5-point scale. Here's why that's strange. R3 blackouts are normally associated with X-class flares, not M-class. An M5 producing R3 level ionospheric effects is like a Category 2 storm producing Category 4 flooding. The category is real, the damage is real, they just don't match. So what happened? There are a few possible explanations and none of them are mutually exclusive, which is part of what makes this uncomfortable. The first involves the GOES satellite measurement system itself. GOES, the Geostationary Operational Environmental Satellite, measures solar X-ray flux in 2 channels, 1.8 angstroms and 0.5 to 4 angstroms. The flare classification is based primarily on the 1.8 angstrom channel, but solar flares don't emit uniformly across the X-ray spectrums. Some flares are spectrally harder than average, meaning they push more energy into the shorter wavelength, higher energy X-ray range. If this flare had an unusually hard spectrum, more energy in the channels that most aggressively ionize the D layer, it could produce radio blackout effects significantly stronger than the headline classification number would suggest. The M5 label reflects the peak flux in one channel. The ionosphere experienced the full spectrum. The second explanation involves the state of the ionosphere at the moment of impact. The ionosphere isn't a fixed, predictable medium. Its density, structure, and susceptibility to disruption vary with season, time of day, geomagnetic conditions, and, critically, with the radiation environment that has been building over the past several days. We'll get to that radiation buildup in more detail shortly. But the relevant point here is that an ionosphere already stressed by 8 days of elevated particle flux may respond more severely to a given X-ray input than a baseline ionosphere would. You're not hitting a clean target, you're hitting a target that's already been worked over. The third possibility is the one that should make everyone watching this a little uneasy. The recorded M5 classification might simply be the number that the instrument captured at the peak moment of measurement, and the actual peak intensity, occurring over a slightly different time window or at a slightly different spectral peak, might have been higher. This isn't as rare as it sounds. There are documented historical cases where post-event analysis revised a flare classification upward once full spectral data was integrated. We may be looking at one of those cases, and here's why this matters for the central thread, for the coronal mass ejection that's already in transit. Flare intensity and coronal mass ejection energy are not perfectly correlated, but they're not independent either. A flare that is more energetic than its official classification suggests could be associated with a coronal mass ejection that is more energetic than our current models are accounting for. We're already working with a coronal mass ejection moving at 1,872 kilometers per second. If the driving event was stronger than classified, the coronal mass ejection's magnetic field configuration could be more complex, more compressed, and more geo-effective than we're currently modelling. The Sun doesn't follow our categories approximate the Sun, and right now the approximation may be running slightly behind the reality. Part 4. The timeline has already started. Let's talk about where this coronal mass ejection is right now, because already in transit isn't just a phrase, it's a countdown. The coronal mass ejection was launched at approximately 0300 Coordinated Universal Time. We know this from the Type 2 radio emission timing. At 1,872 kilometers per second, we're dealing with a transit time to Earth of roughly 24 to 36 hours, with all the usual caveats about deceleration through the interplanetary medium. The working estimate from space weather forecasters places potential arrival somewhere in the range of a late March 31st to early April 1st. Not next week, not in a few days, tomorrow. Possibly into the next calendar day. The clock is already running. But here's the complication with that transit estimate. Coronal mass ejections don't travel through empty space. They travel through the solar wind, a continuous stream of charged particles flowing outward from the sun. And the solar wind has its own speed. Right now, the ambient solar wind is running at approximately 464 kilometers per second. That's already elevated above the typical baseline of around 400 kilometers per second. When a fast coronal mass ejection plows into an already accelerated solar wind ahead of it, a few things happen that affect the impact prediction. First, the coronal mass ejection will decelerate as it pushes through the denser than average solar wind structure ahead of it, but the deceleration will be somewhat less efficient than it would be in a slow, solar wind environment, which means it stays fast longer. Second, the leading edge of the coronal mass ejection compresses the solar wind ahead of it into what's called a sheath region, a turbulent zone of compressed plasma and tangled magnetic field that arrives at Earth before the main coronal mass ejection body does. The sheath region can itself trigger geomagnetic effects, sometimes significant ones, before the main event even arrives. In other words, the first punch may land before most people realize the fight has started. Now. Here's the variable that determines whether any of this actually matters for Earth, and it's the one we cannot know until the coronal mass ejection is almost upon us: the magnetic orientation, specifically the north-south component of the coronal mass ejection's magnetic field, what scientists call the BZ component. When BZ points southward, it aligns opposite to Earth's own magnetic field, and that creates a coupling effect that allows solar plasma to pour through our magnetospheric defenses. When BZ points northward, it reinforces Earth's magnetic field and largely deflects the impact. A coronal mass ejection with the same velocity, the same density, the same energy, can produce either a severe geomagnetic storm or a near miss, depending almost entirely on which way BZ is oriented when it arrives. And we don't know which way that is, not yet. We won't know until the coronal mass ejection passes the L1 Lagrange point, roughly 1.5 million kilometers from Earth, about 30 to 60 minutes before impact. At 1,872 kilometers per second, 30 to 60 minutes is not a planning window, it's a notification. And here is where the timeline intersects with something that shifts this from a space weather story into something significantly more consequential. The Artemis II mission, 4 human beings, including the first woman and first person of colour scheduled to fly beyond low Earth orbit, is currently slated for a launch window that places the crew outside Earth's magnetosphere during the period when this coronal mass ejection may arrive. We're going to come back to that in detail, but I want you to hold that fact right now as we look at the transit window. Because the coronal mass ejection isn't travelling toward an abstract Earth, it's travelling toward an Earth that, in the next 43 hours, may be sending 4 people into the precise zone where a fast coronal mass ejection's radiation effects are most dangerous and least shieldable. The shot was fired at 0300 Coordinated Universal Time, the bullet is in the air, and the target is a lot more complicated than just a planet. Part 5. 8 Days of Invisible Stress. Before the flare happened this morning, before the coronal mass ejection launched, something else was already happening in Earth's orbital environment. Something that has been accumulating quietly for 8 straight days, and that most space weather coverage isn't connecting to today's event. Since March 22nd, electron flux levels in the radiation belts surrounding Earth have been continuously elevated above 1,000 particle flux units. The peak measurement recorded in this period hit 3,750 particle flux units, a level that NOAA classifies as high. This is the kind of sustained radiation exposure that satellite operators worry about in a very specific, very practical way, and understanding why requires understanding something about how satellites actually fail. When energetic electrons, and we're talking electrons with energies in the tens to hundreds of kilo-electron-volt range, bombard a satellite, they don't just bounce off, they penetrate into the dielectric materials that make up a satellite's internal structure. Insulating layers, circuit board substrates, solar cell components. Once embedded, these electrons build up a static charge inside the material itself, not on the surface, where it could dissipate harmlessly inside. And internal charging is dangerous precisely because it doesn't discharge immediately. It accumulates. Over hours, over days, it builds toward a threshold, and then it discharges suddenly. An arc, a spark, a nanosecond event that can permanently damage a microprocessor, corrupt a memory system, or, in worse cases, cause a component failure that ground controllers can't diagnose or recover from. Think about what it means to bend a piece of metal back and forth. Once isn't a problem. 10 times isn't a problem. But each bend is accumulating microscopic stress in the material. You don't know which bend will be the one that snaps it. 8 days of continuous electron flux at elevated levels is the equivalent of bending the metal repeatedly, thousands of times, before the most energetic solar event of the current period has even arrived. The SWPC, the Space Weather Prediction Center, has been issuing serial alerts for this condition throughout the week. It's been monitored, it's been tracked. What it hasn't been is resolved. Because elevated radiation belt flux doesn't switch off when someone notices it. It dissipates on its own schedule, determined by the geomagnetic conditions and solar wind environment, both of which are about to change significantly if this coronal mass ejection is Earth-directed. Newer satellites, designed after the lessons learned from previous radiation belt events, tend to be built with better internal electrostatic discharge protection. But low Earth orbit is now populated with thousands of satellites across multiple generations of design. Some are hardened, some are not. Some are operating on nominal performance margins that don't account for 8 days of continuous pre-stress, followed by a coronal mass ejection impact. And this is where today's event stops being a standalone solar story and becomes something more complex. We're not looking at a fresh system encountering a solar disturbance. We're looking at a system that has been absorbing invisible stress for over a week, now facing a potential direct hit from the fastest coronal mass ejection of the current solar cycle. Part 6. The 2.8-day clock. There's a number that came out of a European Space Agency analysis that I want to introduce here because it reframes the orbital situation in a way that ground-level coverage simply hasn't captured. 2.8 days, that's the current estimated time to the first catastrophic collision event if every satellite operator in low Earth orbit simultaneously lost the ability to perform collision avoidance maneuvers. 2.8 days from a total loss of maneuver capability to a statistically expected first catastrophic impact. To understand why that number matters, you need to know what it used to be. In 2018, the same type of analysis produced a figure of 121 days. We've gone from 4 months to under 3 days in about 6 years. Not because satellites got worse at maneuvering, because the population of objects in low Earth orbit grew faster than the margin of safety. There are currently approximately 11,800 active satellites in low Earth orbit. Add the debris, defunct satellites, spent rocket stages, fragmentation pieces from past collisions and anti-satellite tests, and the number of tracked objects exceeds 25,000. Close approaches between tracked objects now occur approximately every 22 seconds globally, not per day, per minute. Every 22 seconds, somewhere above your head, 2 tracked objects pass within a dangerous proximity threshold of each other. Most of those conjunctions result in nothing. Operators assess. They maneuver when necessary. The system works when it works. But here's the critical dependency that connects this directly to the coronal mass ejection in transit right now. Collision avoidance depends on 2 things: knowing where objects are and being able to move your satellite when necessary. Space weather disrupts both. Ionospheric disturbances degrade the GPS-based tracking systems that feed orbital position data to operators. Solar energetic particle events can cause single event upsets in satellite processors, temporary glitches, anomalous commands, unexpected resets. And in the specific case of a significant geomagnetic storm, the upper atmosphere expands outward, increasing drag on low-orbiting objects in a way that changes their orbital paths in real time, faster than standard propagation models can update. The 2.8-day figure isn't the expected timeline to disaster under normal conditions. It's the expected timeline to disaster if the system's ability to track and maneuver breaks down, even partially, even temporarily. A coronal mass ejection with a southward BZ component creating a G3 or G4 geomagnetic storm could produce exactly that kind of partial, temporary breakdown. Not for all operators, not for all systems, but for enough of them at the same time, during a period when the conjunction rate is already 1 every 22 seconds, that the probability of a collision during a 24-hour disruption window runs at approximately 30%. 30% isn't certainty, but it isn't theoretical either. And it's the probability sitting inside that 2.8-day clock, which is itself sitting inside the transit window of a coronal mass ejection, we can't yet locate precisely. Part 7. Real precedent, not theory. Some people hear solar flare damages satellites, and their brain files it under possible future concern. This already happened 4 years ago, and the numbers are specific enough that no one should be treating this as a hypothetical. In February of 2022, SpaceX launched 49 Starlink satellites into a low deployment orbit. Standard procedure. They were supposed to raise their altitude gradually over subsequent days and join the operational constellation. They never got the chance. A G1 geomagnetic storm, that's the weakest category on the 5-point geomagnetic storm scale, caused the upper atmosphere to expand. Thermospheric density at the deployment altitude increased by somewhere between 20 and 50%. The drag on the newly launched satellites multiplied. The satellites, not yet at operational altitude and running in safe mode with limited maneuverability, couldn't compensate. 38 of the 49 satellites re-entered the atmosphere and burned up. 38 spacecraft, a G1 storm, the weakest category. The mechanism matters here. During geomagnetic disturbances, energy from the solar wind gets deposited into the upper atmosphere, the thermosphere and exosphere, heating it and causing it to expand outward. For satellites in very low orbits, even a modest increase in atmospheric density dramatically increases drag, because drag force scales with atmospheric density. A 50% increase in density at an altitude where drag is already meaningful can, in a short period, alter an orbit enough to cause uncontrolled re-entry. The Starlink satellites weren't hit by radiation. They weren't struck by debris. They were slowed down by thicker air that was thickened by a minor solar storm that most people never heard about. Now bring that precedent forward to today. The coronal mass ejection currently in transit is moving at 1,872 kilometers per second. The storm that destroyed 38 Starlink satellites was triggered by a geomagnetic disturbance significantly less energetic than what a direct impact from a fast coronal mass ejection could produce. The current low Earth orbit population has grown substantially since 2022. More satellites, more deployment operations, more objects in the altitude range where atmospheric expansion effects are most severe. And we are 8 days into an elevated radiation environment that has already been stressing orbital electronics, sitting on the edge of an event that could amplify every one of those existing vulnerabilities simultaneously. The 2022 event cost SpaceX an estimated $100 million and lost 38 spacecraft in a single night. A G1 storm, one category. What happens at G3 or G4 to a constellation that is now 10 times larger, and an orbital environment that is orders of magnitude more crowded? Part 8. Orbital density has crossed a threshold. Here's a concept that I want you to understand because it changes how you think about the orbital risk from today's event, and it doesn't get enough attention in mainstream space weather coverage. The orbital environment around Earth is no longer a static backdrop that things move through. It has become a dynamic system, one that has, in the past several years, crossed a threshold of density beyond which the interactions between objects are no longer just coincidental. They're structural. There are approximately 11,800 active satellites in low Earth orbit right now. Starlink alone accounts for roughly 7,000 of those. That number is growing. The plans currently approved or in progress across SpaceX, Amazon's Kuiper constellation, OneWeb, and several other operators would add tens of thousands of additional satellites over the next decade. Each launch increases the close approach frequency. Each increase in close approach frequency increases the probability that a temporary disruption in tracking or maneuvering capability will result in an actual collision during that disruption window. A satellite collision doesn't just destroy two satellites. It creates debris, hundreds to thousands of fragments, depending on the size and relative velocity of the impacting objects. Those fragments spread into a shell around the orbit altitude of the collision. Some fragments re-enter quickly, some stay in orbit for years, decades, or in higher orbits, centuries. Each fragment is a new conjunction risk for other satellites in similar orbits. This chain reaction, A collision producing debris that increases the probability of further collisions is what scientists call the Kessler syndrome at its full theoretical development. But you don't need full Kessler cascade to cause serious operational problems. One collision in the Starlink orbital band could produce enough debris to force hundreds of emergency maneuvers across the constellation, consuming fuel reserves, disrupting service, and potentially causing secondary close approaches during the avoidance maneuvers themselves. The European Space Agency has debris removal missions planned with a 2026 timeline. They exist because the people who manage orbital space have accepted that the population of non-maneuverable debris is already beyond what passive management can handle. We are scheduling cleanup operations for a mess that keeps growing while the cleaning equipment is still being built. And so when we talk about today's coronal mass ejection, when we talk about the transit of an energetic solar event toward an Earth whose orbital shell is operating at this level of conjunctional density, with electronics already stressed by 8 days of elevated radiation, with a 2.8-day margin before a statistical first collision under disrupted conditions, we're not talking about a solar story with orbital implications. We're talking about an orbital system that was already functioning at the edge of its tolerance, about to be tested by the most energetic solar event in the current observational window. The coronal mass ejection doesn't need to be catastrophic to matter. It just needs to be disruptive enough, at the wrong moment, to push a system that's already threading the needle. Part 9. The 3 failure channels. If this coronal mass ejection is Earth-directed and arrives with a southward BZ component, the impact won't announce itself through a single dramatic failure. It will move through 3 distinct channels simultaneously, and the interaction between those channels is where the real danger lives. The first channel is direct radiation damage. Fast coronal mass ejections carry solar energetic particles, protons and heavy ions, accelerated to significant fractions of the speed of light by the shock ahead of the ejection. These particles don't care about Earth's magnetic field the way slower particles do. At sufficient energies, they penetrate to polar latitudes and sometimes deeper, depositing radiation doses in satellite electronics, degrading solar cell efficiency, and, in the case of humans outside Earth's magnetic protection, presenting a genuine acute radiation exposure risk. The particle event from a coronal mass ejection, moving at this speed, can precede the main body of the ejection by hours, which means radiation effects may begin before the geomagnetic storm does. The second channel is communication disruption. We already saw this at 0306 with the HF radio blackout. A geomagnetic storm, especially a major one, disrupts the ionosphere in ways that affect not just HF radio but also GPS signals, satellite communication links and ground-based radar systems. GPS works by measuring extremely precise timing signals from satellites. The ionosphere introduces variable time delays in those signals. Under normal conditions, those delays are well characterized and corrected for. During a major geomagnetic storm, the ionosphere becomes turbulent and irregular in ways that current correction models can't fully account for, degrading GPS accuracy for anything from navigation to the orbital tracking systems that feed collision avoidance calculations. At the exact moment when satellite operators need the most accurate position data to make avoidance decisions, their position data becomes less reliable. The third channel is atmospheric drag, and we already know what this one does, because we watched it happen to 38 Starlink satellites in 2022. A major geomagnetic storm deposits energy into the thermosphere, expanding it outward, increasing drag on low-orbiting objects in a way that changes their predicted orbital paths faster than ground-based tracking can update. Operators make avoidance maneuver decisions based on predicted future positions. If the predicted positions are wrong because the atmospheric model is running behind real-time conditions, operators may maneuver when they don't need to, or fail to maneuver when they do. Now consider all 3 of these channels operating at the same time, on the same orbital population, on the same day. Communication disruption reduces the accuracy of the position tracking that feeds avoidance decisions. Atmospheric drag is simultaneously changing the actual positions of thousands of objects in ways the models aren't capturing in real time. And radiation events are causing single event upsets in the processors, running the avoidance logic on the satellites themselves. These aren't 3 separate problems. They're 3 legs of the same table, and the table collapses when all 3 are kicked simultaneously. Redundancy in space systems is designed around individual failure modes. It is not designed around correlated simultaneous failure across multiple independent systems. The sun doesn't send targeted attacks, it sends waves, and waves hit everything at once. Part 10. The compression effect. There is a subtlety in coronal mass ejection impact physics that forecasters understand, but that public coverage almost never explains properly, and it is relevant to today's event in a very specific way. It is the kind of detail that sits between the headline and the reality, and in space weather, that gap is where the surprises live. The coronal mass ejection is not travelling through empty space. This is the first thing most coverage gets wrong, or simply skips over because it complicates the narrative. When we talk about a coronal mass ejection moving at 1,872 km per second toward Earth, the instinct is to imagine it crossing a clean, frictionless void, a billiard ball fired across a perfect table. That is not what is happening. The coronal mass ejection is moving through the solar wind, which is itself a continuous outflow of plasma, streaming outward from the sun in all directions, carrying within it an embedded magnetic field, the interplanetary magnetic field, that twists and fluctuates as it propagates through space. The solar wind is not a calm river. It is a dynamic, structured medium with fast streams and slow streams, regions where plasma is compressed against itself, and regions where it has expanded and thinned. Its internal structure changes on timescales of hours to days, and everything the coronal mass ejection does as it travels through that medium is shaped by what it finds ahead of it. Here is where the physics gets interesting, and where the risk for today's event becomes more nuanced than the headline speed suggests. When a fast coronal mass ejection overtakes slower solar wind plasma ahead of it, it does not simply push through it cleanly, it compresses it. The coronal mass ejection's leading edge acts like a plough, driving the slower plasma ahead of it into a denser, hotter, more magnetically tangled structure. This compressed zone, called the sheath region, forms between the coronal mass ejection's driven shock and the leading edge of the ejection body itself. It is a region of turbulent compressed plasma that arrives at Earth before the main coronal mass ejection body does, before the headline act, before the structure that most models are tracking as the primary event. The opening act is the sheath, and the sheath does not behave predictably. Right now, the ambient solar wind is running at approximately 464 km per second. That is above the typical baseline of around 400 km per second. On an ordinary day, a slightly elevated solar wind speed would be a minor footnote in a space weather briefing. But today, it is not a footnote, it is a multiplier. A faster than normal solar wind ahead of the coronal mass ejection means there is more energetic material for the ejection to plough through as it travels inward. The compression of that faster moving material will be more violent than it would be in a slow, solar wind environment. The sheath region that forms ahead of this coronal mass ejection will be denser, more magnetically intense, and more structurally complex than a sheath forming in a quiet solar wind would be. And the magnetic fields within that sheath, fields that have been compressed and tangled by the collision of two fast-moving plasma structures, can reach intensities significantly higher than either the pre-existing solar wind or the coronal mass ejection body alone would produce. Now here is the critical point, and this is the one that determines whether any of this produces a significant geomagnetic storm or slides past without major consequence. Within the sheath region, the BZ component of the magnetic field, the north-south orientation of the interplanetary magnetic field, can flip direction multiple times as the compressed and tangled structure passes over Earth. BZ is the single most important variable in determining how Earth's magnetosphere responds to an incoming solar structure. When BZ points southward, it connects with Earth's northward pointing magnetic field through a process called magnetic reconnection, effectively opening a door in the magnetosphere through which solar plasma can pour. When BZ points northward, that door stays largely closed, and the storm impact is dramatically reduced. A coronal mass ejection with a sustained southward BZ can drive a major geomagnetic storm. The same coronal mass ejection with a northward BZ can produce almost nothing. The problem with the sheath region is that BZ within it is not stable. It fluctuates. It flips. An operator watching the real-time solar wind data at L1 might see BZ swing southward, triggering protective protocols, then watch it swing northward, then southward again, multiple times, before the main coronal mass ejection body even arrives. The storm does not follow a clean onset peak and recovery curve the way a textbook diagram suggests. It pulses, it surges, it partially recovers, then surges again. For satellite operators trying to determine whether to safe their spacecraft, for grid operators trying to decide whether to preemptively reduce load on long transmission lines, for launch directors evaluating a go or no-go decision against a dynamic and fluctuating radiation environment, a complex irregular arrival profile is significantly harder to manage than a clean, predictable one. The historical record makes this concrete. The Halloween storms of 2003, still among the most severe space weather events of the modern satellite era, produced geomagnetic intensities that exceeded the initial model predictions, in large part because the solar wind environment ahead of the arriving coronal mass ejections was already disturbed by earlier activity. The coronal mass ejections did not arrive into a clean medium. They arrived into a preconditioned environment, and the interaction amplified the outcome. The St. Patrick's Day storm of 2015 followed a similar pattern. Initial forecasts predicted a moderate event. The interaction between the arriving coronal mass ejection and the pre-existing solar wind structure ahead of it drove the storm to levels that caught some operators off guard. Power grid anomalies were reported. Satellite operators issued anomaly reports. GPS accuracy degraded across regions that hadn't been flagged as high risk in the pre-event forecast. Both of those events occurred in solar wind environments that were elevated but not dramatically so. The solar wind ahead of today's coronal mass ejection is already running above average. The coronal mass ejection itself is travelling at nearly 4 times normal speed, meaning the compression at its leading edge will be proportionally more energetic than the events that produced those historical surprises. The interaction between this coronal mass ejection and the solar wind structure it is ploughing through, if it is Earth-directed, will not be a simple addition of their individual effects. It will be a compression event, a collision between 2 fast-moving plasma structures in a confined interplanetary corridor, producing a sheath of amplified, tangled magnetic field that arrives at Earth before the main event, behaves unpredictably during its passage, and potentially drives storm conditions that exceed what the coronal mass ejection body alone would have produced. There is a principle in physics and in engineering that compressed systems release energy faster and less predictably than unconstrained ones. A spring that's already partially compressed takes less additional force to reach its failure point. A material already under stress fractures at loads that would not affect arrested material. The solar wind environment between the Sun and Earth right now is already moving faster than normal, already carrying a magnetic field that has been processed by 8 days of elevated solar activity, already primed by whatever disturbed conditions produced this morning's eruption. The coronal mass ejection is not arriving into a neutral medium. It is arriving into a medium that is already leaning in its direction. That is what makes the compression effect the detail that matters most right now, and the detail that the public summary of this event is almost certainly going to miss. The speed of the coronal mass ejection is the number everyone will report. 1,872 kilometers per second, 4 times normal. That number is real and it is significant. But the speed of the coronal mass ejection tells you how fast the event is moving. The state of the solar wind ahead of it tells you what it's going to do when it gets here. And right now, what it's going to do when it gets here is compress a medium that is already elevated, amplify a sheath region that was already going to be turbulent, and deliver a magnetic field orientation that will fluctuate unpredictably across the most consequential variable in the entire impact calculation, all before the main event even arrives. The sheath gets there first, and the sheath is already forming. Part 11. The forecast is already outdated. Let's talk about something uncomfortable. The decision makers who need to act on this event, the satellite operators, the launch directors, the grid managers, the space agency flight directors, are working with forecast models that were built for a solar environment that no longer matches what's happening. Not because the models are poorly designed, not because the scientists running them aren't talented, but because the Sun is a 4.6 billion-year-old nuclear reactor operating on its own schedule, and our ability to predict its behaviour in real time is still, in the most consequential moments, running a few steps behind. The NOAA Space Weather Prediction Centre forecast issued at 0030 Coordinated Universal Time this morning described a quiet sun. That forecast was written by professionals using the best available data from the best available monitoring network on Earth. Less than 3 hours later, an M5 solar flare blacked out half the planet's radio communications simultaneously, and a coronal mass ejection travelling at 1,872 km per second was already in transit toward an unconfirmed destination. The gap between those two realities, between quiet sun and half the planet just lost radio contact, is not a gap created by incompetence. It is a gap created by the fundamental limitations of trying to forecast a dynamic, three-dimensional, magnetically complex stellar object from instruments positioned at the edge of its influence zone. But the gap is real. And real gaps have real consequences. Consider what happened in the hours between that forecast and this morning's eruption. Satellite operators across the world received a prediction of quiet conditions and made operational decisions accordingly. Some of those decisions were about safing procedures, whether to put satellites into a protective low-power mode or keep them in full operational configuration. Some were about constellation management, which satellites to task for high-priority operations, which to schedule for routine maintenance windows. Some were about maneuver scheduling, when to execute conjunction avoidance burns, when to hold, when to let the orbital mechanics run without intervention. All of those decisions were made in good faith, based on a forecast that was accurate at the time it was written and wrong by the time anyone acted on it. Space operations are not like adjusting a thermostat. This is the detail that people outside the industry consistently underestimate. Moving a satellite into a protective orientation requires commanding a spacecraft that may be on the other side of the Earth from its ground station, waiting for a communication window, uplink the command sequence, confirm execution, and monitor the response, all before the event that requires the protection actually arrives. Scheduling a collision avoidance maneuver requires calculating the optimal burn parameters, coordinating with other operators who may be adjusting their own trajectories in response to the same conjunction, notifying the relevant tracking agencies, and executing with enough lead time that the maneuver actually changes the predicted close approach geometry before the close approach moment passes. A forecast that shifts from quiet to major event possible in the span of 3 hours doesn't just update the weather picture. It compresses every decision window for every operator who was already committed to a plan built around the previous forecast. Some of those commitments can be reversed, some cannot. And in an orbital environment operating at a conjunction frequency of 1 close approach every 22 seconds, the ones that cannot be reversed are the ones that matter. The broader issue, and this is the one that the space weather community has been wrestling with for years without a fully satisfying answer, is the gap between forecast latency and solar event dynamics. Our best current solar weather models are genuinely impressive instruments. The WSA-NLIL plus cone model, run operationally at NASA's Community Coordinated Modeling Center and at NOAA's Space Weather Prediction Center, takes coronagraph observations of a coronal mass ejection's initial shape and speed and propagates it through a simulated solar wind to predict arrival time at Earth. Ensemble runs produce probability distributions rather than single-point forecasts. The models have real skill at determining whether a coronal mass ejection will hit Earth at all, and at estimating arrival times with uncertainty ranges that typically shrink from plus or minus 12 hours at launch to plus or minus a few hours as the event approaches the L1 monitoring point. For the question of is something coming and roughly when, the current modelling architecture does a reasonable job. What the models are significantly less capable of is predicting the internal magnetic structure of the arriving coronal mass ejection, specifically the BZE orientation, the north-south component of the magnetic field embedded within the ejection body, with any useful accuracy until the event is essentially at Earth's doorstep. The physics of this limitation is not mysterious. The magnetic structure of a coronal mass ejection evolves as it propagates through the solar wind. It interacts with the ambient field, it rotates, it distorts. The initial magnetic configuration at the Sun, which is itself difficult to measure directly, is not reliably preserved through 150 million kilometers of interplanetary transit. Current models can make educated guesses about BZ orientation based on the source region's magnetic geometry and the coronal mass ejection's initial structure, but those guesses carry uncertainty ranges wide enough to span from major storm to near miss for the same event. Useful predictive skill on BZE, the kind of confidence that would actually change a launch decision, or trigger a preemptive grid protection protocol doesn't arrive until the coronal mass ejection passes the ACE spacecraft at L1, approximately 1.5 million kilometers from Earth. At 1,872 kilometers per second, that translates to roughly 30 to 60 minutes of lead time between we know what's coming and it's here. 30 minutes. For the most consequential variable in the entire impact equation, the people responsible for making protective decisions have approximately 30 minutes of actionable warning. And that 30 minutes doesn't arrive at the beginning of the decision window. It arrives at the end. Everything before it is probability management, educated guessing with error bars, planning for scenarios rather than confirmed outcomes, making reversible decisions where possible, and hoping the irreversible ones don't matter. Apply that directly to what is happening right now. If this coronal mass ejection is Earth-directed, the satellite operators responsible for protecting 11,800 active orbital assets won't have confirmation of that until the transit window is nearly closed. The Artemis II launch team evaluating a go or no-go decision against a radiation environment that could be either benign or dangerous won't know which until the margin between we could still hold and the window has passed has already narrowed past the point of comfortable decision-making. The grid operators responsible for protecting long-haul transmission infrastructure from geomagnetically induced currents won't know the storm intensity until the storm is already beginning to develop. And every one of those decision makers is working against a backdrop of 8 days of accumulated radiation stress, a 2.8-day orbital collision window, and a forecasting architecture that is doing the best it can with instruments positioned at the edge of a system moving faster than the instruments can fully characterize. There is a phrase in aviation safety culture, the error chain. Individual mistakes rarely cause accidents. What causes accidents is a sequence of individually manageable errors that compound each other until the combined effect exceeds the system's ability to absorb and recover. A forecast that says quiet when the sun is about to erupt is one link. Operators making irreversible decisions based on that forecast is another link. A coronal mass ejection whose most dangerous characteristic won't be confirmed until 30 minutes before arrival is another link. An orbital environment already operating at the edge of its conjunction tolerance is another link. 4 humans preparing to leave Earth's magnetic protection during a window that overlaps with an unconfirmed coronal mass ejection arrival is another link. None of these links, in isolation, is a catastrophe. Chains don't break at their strongest point. They break where the links connect. What we are watching right now is not a story about a bad forecast. It is a story about a system operating at the limit of its predictive capability, at a moment when the cost of prediction failure is higher than it has been in years. The forecasters are not the vulnerability. The gap between what the forecasting system can deliver and what the decision-making system requires is the vulnerability. And that gap right now is exactly the width of the 30-minute window between confirmation and arrival. 30 minutes of warning is not 30 minutes of protection. It is 30 minutes of confirmation that what you are hoping wouldn't happen is, in fact, happening. And by the time you have that confirmation, most of the decisions that mattered have already been made. Part 12. The limb versus Earth-facing coin flip. Everything we have discussed in the last 3 parts hinges on a single unresolved question. Not a complicated question. Not a question buried in technical jargon or accessible only to specialists. A binary question with 2 possible answers, one of which makes most of what we have covered an academic exercise in near-miss analysis, and one of which makes all of it urgently, immediately relevant. I want to be direct about what we know, what we don't, and what the difference between those 2 answers actually means for everything sitting in the path of this coronal mass ejection. The question is simple. Is this coronal mass ejection aimed at Earth? We do not yet have a confirmed answer. And the reason we don't is worth understanding, because it explains why the next 6 to 12 hours are the most consequential window in this entire event. More consequential in some ways than the impact itself. Start with what we know about the source. The flare that triggered this morning's radio blackout has been officially logged in the NASA Donkey database with a source designation of NA. Not applicable, meaning unidentified. The 2 candidate regions currently under analysis are region 4397, sitting at approximately north 15 degrees, west 95 degrees, and region 4398 at south 16 degrees, west 97 degrees. Both of those coordinates place the candidate source regions at or very near the western solar limb, the extreme edge of the Sun's visible disk as seen from Earth. And the location of the source region is the single most important geometric input into the trajectory calculation for the coronal mass ejection it produced. Here is why limb positioning matters so fundamentally. The Sun rotates. Active regions move across its face over a period of roughly 2 weeks, as they rotate from the eastern limb, across the Earth-facing disk, to the western limb, and then behind the Sun entirely. A region sitting at west 95 to west 97 degrees is near the end of its Earth-facing rotation, almost around the corner, about to disappear behind the limb entirely. When an active region at that position erupts and launches a coronal mass ejection, the ejection is launched in a direction that follows the local magnetic geometry of that region, and a region near the western limb is oriented such that its eruption direction points significantly west of the Sun-Earth line. Think of it geometrically. If the Sun is at the centre and Earth is directly to the right, a western limb eruption is firing from the upper right edge of the Sun, angled away from Earth rather than toward it. A coronal mass ejection launched from a confirmed western limb position would most likely travel through interplanetary space in a direction that misses Earth's orbital position, or at most delivers a glancing blow from the western flank. The shock ahead of the ejection might still reach Earth, might still produce minor to moderate geomagnetic disturbances as it sweeps past, might still elevate the radiation environment for a period of hours. But the main body of the ejection, the magnetically coherent flux rope structure at its core, the part that carries the highest field intensities and the most sustained southward BZ potential, would slide past us and continue into the outer solar system. The 11,800 satellites, the 2.8-day collision window, the Artemis II crew, the power grid infrastructure, all of it would face elevated but manageable conditions rather than a direct impact scenario. That is the better of the two possible answers, and if the candidate regions at the western limb are confirmed as the source, it is the likely answer. But there are reasons the answer isn't confirmed yet, and those reasons are not trivial. The first is the NOAA designation itself. For a flare of this magnitude, M5 class, R2 to R3 radio blackout, fast coronal mass ejection, an unidentified source is unusual enough to warrant genuine uncertainty, rather than a defaulted assumption. If the source were clearly and unambiguously one of the two limb-positioned candidate regions, the identification would typically be more straightforward. The fact that it isn't suggests either that the limb positioning is obscuring the source identification in ways that make confirmation difficult, or that the source is something other than the catalogued candidates, an emerging region that hadn't yet been assigned a tracking number, a complex multi-source eruption, or the possibility that the solar community is most reluctant to assign without clear evidence. That possibility is a behind-the-limb event, a solar eruption originating from a source region that has already rotated past the western limb, beyond the edge of what Earth-facing instruments can directly observe, but energetic enough that its shockwave propagated around the limb and produced observable signatures at Earth-facing longitudes. Behind-the-limb events are not common, but they are documented. And they are important for one specific reason. An eruption originating from behind the western limb, while it sounds like it should be pointing even further away from Earth than a limb event, can in some geometries produce a coronal mass ejection whose propagation path in the interplanetary medium curves back toward the Sun-Earth line more than a simple geometric projection would suggest. The solar wind structure, the Parker spiral geometry of the interplanetary magnetic field, and the initial eruption geometry all interact in ways that make behind-the-limb trajectory predictions particularly uncertain. This is precisely where Stereo A becomes the instrument that this entire story is waiting on. The Solar Terrestrial Relations Observatory, Stereo A, is positioned in an orbit that places it approximately 15 to 20 degrees ahead of Earth in solar longitude. From that vantage point, regions that are at or just beyond Earth's western limb are shifted toward the centre of Stereo A's field of view. A source region sitting at west 95 degrees from Earth's perspective is at roughly west 75 to 80 degrees from Stereo A's perspective, still near the limb but more observable. And critically, the coronagraph aboard Stereo A, an instrument that blocks out the solar disk to reveal the faint structure of the corona and any coronal mass ejections propagating through it, provides a side-angle view of the ejection structure that Earth-facing coronagraphs cannot. The diagnostic is geometrically elegant in its simplicity. A coronal mass ejection launched from a western limb source, travelling away from Earth, will appear in stereo-A's coronagraph data as an asymmetric off-axis structure, a bright arc expanding outward predominantly on one side of the solar disk, clearly offset from centre. An Earth-directed coronal mass ejection, travelling toward the Sun-Earth line and therefore roughly towards stereo-A's general direction as well, will appear as a halo event or partial halo, a ring of brightness expanding outward around the entire circumference of the solar disk, because the ejection is moving toward the observer and its expanding shell appears as a surrounding ring rather than a one-sided arc. Halo in the coronagraph means Earth-directed. Asymmetric arc means not Earth-directed. The data, when it arrives and is processed, will answer the binary question with a level of clarity that no other currently available observation can match. The stereo-A coronagraph data is coming. The pipeline between raw instrument data and operational forecast product involves transmission, processing, quality control, and model integration, steps that take time even when everything is functioning nominally. Right now, somewhere in that pipeline, the data that answers the most important question in this event is being processed, and while it moves through that pipeline, the coronal mass ejection is continuing its transit at 1,872 kilometers per second, covering approximately 6.7 million kilometers every hour, closing the distance between its current position and Earth's orbital path with complete indifference to the processing timelines of the instruments trying to characterize it. 6 to 12 hours. That is the working estimate for when stereo-A data and initial propagation model runs should converge on a trajectory estimate with sufficient confidence to answer the Earth-directed question definitively. 6 to 12 hours during which every decision that depends on that answer, satellite safing, launch go or no-go, grid protection protocols, crew radiation risk assessment, is being made in the absence of the one piece of information that would make those decisions straightforward. At the end of those 6 to 12 hours, one of two things happens. The data confirms a western limb trajectory, the coronal mass ejection slides past Earth's flank, and everything we have discussed becomes a detailed case study in how close the margins already are even when the main event misses. Or the data confirms an Earth-directed trajectory, the response window collapses to the hours that remain before arrival, and every system we have described, the stressed orbital environment, the weakened satellites, the astronauts at the edge of the magnetosphere, the forecasting architecture running 30 minutes behind the most consequential variable, gets tested simultaneously, in real time, with no opportunity to reset. Everything in this story converges on that determination. The compression effect in the sheath region, the 30-minute BZ warning window, the 2.8-day collision clock, the Artemis II launch decision, the 8 days of radiation stress already banked into every circuit in orbit. All of it is downstream of one question that a spacecraft 15 to 20 degrees ahead of Earth in solar longitude is, right now, in the process of answering. We are waiting for the data. The coronal mass ejection is not waiting with us. Part 13. The Artemis II timing problem. At some point in the next 43 hours, depending on final launch readiness confirmation, 4 human beings are scheduled to climb into an Orion spacecraft, sit on top of the most powerful rocket ever successfully flown, and depart Earth's magnetic shield for the first time since the Apollo era. Let that land for a moment. 53 years. That is how long it has been since any human being travelled beyond the protection of Earth's magnetosphere. An entire generation of spaceflight, the shuttle era, the International Space Station, every crewed mission flown since the last Apollo astronaut splashed down in December of 1972, has taken place inside the magnetosphere's protective bubble. Everything changes with Artemis II. The mission carries 4 people whose names deserve to be said clearly, because they are the specific human beings whose safety is now entangled with the trajectory of an unidentified coronal mass ejection, travelling at 1,872 kilometers per second. Commander Reed Wiseman, a NASA astronaut and former International Space Station commander with deep experience in long-duration spaceflight operations. Pilot Victor Glover, who flew to the International Space Station on the first operational Crew Dragon mission, and will become the first person of colour to travel beyond low Earth orbit. Mission Specialist Christina Koch, who holds the record for the longest single spaceflight by a woman and will become the first woman to travel beyond Earth orbit. And Canadian Space Agency astronaut Jeremy Hansen, making his first spaceflight and representing the first non-American to fly on a lunar trajectory mission since the Apollo era. 4 people, 10 days, a free return trajectory around the moon and back, and a departure window that is now sitting directly adjacent to the estimated arrival window of a fast coronal mass ejection whose destination has not been confirmed. The trajectory of the Artemis II mission was planned months ago. Launch windows for lunar missions are not flexible in the way that low Earth orbit launches are. They are determined by the precise geometric alignment of the launch site, the rocket's performance envelope, the moon's orbital position, and the specific trajectory geometry required to achieve the free return path that gives the crew a passive route home if the propulsion system fails at any point in the mission. Miss the window by more than a few hours, and the entire orbital mechanics calculation has to be rebuilt around the next available alignment. The schedule was set, the trajectory was locked, the countdown was proceeding, and the solar weather forecast that underpinned the radiation risk assessment for the launch window was written at 0030 Coordinated Universal Time this morning, hours before an M5 flare blacked out half the planet and a coronal mass ejection launched into interplanetary space from an unidentified source. The radiation environment that the Artemis II crew will encounter beyond the magnetosphere is categorically different from anything experienced by astronauts on the International Space Station, and understanding that difference is essential to understanding why today's event matters specifically for this mission. Inside the magnetosphere, Earth's magnetic field deflects the vast majority of the solar energetic particle flux that the Sun continuously produces. The International Space Station operates at an altitude of approximately 400 kilometers, well within the magnetospheric bubble, and its crew receives radiation doses that are elevated compared to Earth's surface but manageable within established occupational exposure guidelines. The magnetosphere is doing most of the protective work, and it is doing it continuously, invisibly, without any hardware on the spacecraft needing to contribute to the effort. Beyond the magnetosphere, that protection disappears entirely. There is no fallback. The Orion spacecraft has radiation shielding built into its structure, more shielding than the Apollo command modules carried, because 5 decades of engineering progress and a better understanding of the interplanetary radiation environment have informed the design. But shielding a crewed spacecraft against the full range of solar energetic particle energies is a problem that mass constraints make fundamentally unsolvable with current technology. High-energy protons, the primary radiation hazard from solar energetic particle events, require substantial material thickness to stop. Stopping them completely would require a spacecraft so heavy it couldn't be launched. The engineering compromise is to reduce the dose to acceptable levels under normal interplanetary conditions, while accepting that a major solar energetic particle event during the mission would deliver doses that exceed nominal exposure guidelines and could, depending on event intensity and duration, approach levels with acute health consequences. The solar energetic particle environment doesn't wait for a convenient moment. It is driven by the physics of the coronal mass ejection shock, the shockwave ahead of the ejection body that accelerates protons and heavy ions to energies high enough to cross interplanetary space in minutes to hours. A fast coronal mass ejection like the one currently in transit is particularly efficient at this acceleration process. The shock is stronger, the acceleration more energetic, and the resulting particle event can build to dangerous intensities faster than a slower coronal mass ejection would produce. The particle flux can begin rising hours before the main coronal mass ejection body arrives, which means the radiation environment in interplanetary space can deteriorate significantly before any of the other storm effects. The geomagnetic disturbance, the ionospheric disruption, the atmospheric drag increase have even begun. For a crew already in transit beyond the magnetosphere when a major solar energetic particle event begins, the options are limited in ways that ground-based emergency response simply doesn't face. There is no shelter nearby. There is no option to return immediately. A free return trajectory takes the time it takes, governed by orbital mechanics that don't respond to biological urgency. The Orion capsule has a designated storm shelter configuration, a specific arrangement of the crew and spacecraft that places the maximum available shielding material between the crew and the incoming particle flux. It reduces the dose. It does not eliminate it, and the effectiveness of that shelter configuration depends entirely on the intensity and duration of the particle event, neither of which can be predicted with useful precision until the event is already underway. This is the context in which the coronal mass ejection arrival window needs to be understood. The 43-hour countdown to the Artemis II launch window is not running parallel to the coronal mass ejection transit timeline, it is running inside it. The coronal mass ejection's estimated arrival at Earth, late March 31st to early April 1st, sits within or immediately adjacent to the window during which the Artemis II crew could be in transit beyond the magnetosphere. Not coincidentally adjacent, not tangentially related, directly overlapping in a way that places the mission's radiation risk assessment in real-time dependency on the space weather forecast for the next 48 hours. NASA's launch decision process for Artemis II includes space weather as a formal constraint. There are defined thresholds, solar energetic particle flux levels, geomagnetic storm indices, solar wind conditions that feed into the launch commit criteria. If those thresholds are exceeded in the hours before launch, the launch director has the authority and the obligation to call a hold. The system is designed for exactly this kind of situation. What it is not designed for, what no launch commit criteria system can fully account for, is a coronal mass ejection whose trajectory is unconfirmed, whose magnetic orientation won't be known until 30 minutes before arrival, and whose associated particle event potential cannot be characterized until it is already developing. The criteria exist. The data to evaluate them against doesn't fully exist yet, and the window in which the data will become available is compressing toward the window in which the launch decision must be made. There is a further complication that sits beneath the technical discussion and deserves to be named directly. The Artemis program has carried significant schedule pressure since its inception. Development delays, budget cycles, technical certification requirements, and the weight of political expectation around America's return to human lunar exploration have made every launch window feel consequential in ways that go beyond the mission itself. The pressure to maintain schedule is real. It exists. It is not supposed to influence a safety determination, and in the formal structure of NASA's decision-making process, it doesn't have a seat at the table. But it shapes the institutional context in which ambiguous probabilistic safety data gets interpreted. When the data says possible but uncertain risk, the institutional pressure to interpret that as acceptable, rather than reason to hold, is not imaginary. It has to be actively managed. And it has to be actively managed at a moment when the people doing the managing are working with a 30-minute warning window on the most important variable in the risk equation. The coronal mass ejection arrival window overlaps with the Artemis II launch window, not theoretically, not as a worst-case scenario projection, as the current best estimate of when a fast, uncharacterized solar ejection from an unidentified source will reach the vicinity of Earth, and as the current confirmed countdown to the moment when 4 specific human beings are scheduled to leave the only magnetic protection available to them for the next 10 days. There is an event from August of 1972 that every radiation protection scientist working on human space exploration carries as a reference point. It happened in the gap between Apollo 16 and Apollo 17. It defines what the interplanetary radiation environment can produce at solar maximum, and it almost happened while people were out there. We will get to that in the next part. But hold this first. The question of whether those 4 people launch into that environment on schedule is now, as of 0306 this morning, a space weather question. And the answer depends on data that hasn't arrived yet. Part 14, the 1972 near-miss scenario. In August of 1972, the Sun did something that the space age had not yet seen at full intensity, with its instruments properly positioned to measure it. It produced one of the most energetic solar proton events ever recorded, a burst of high-energy particle radiation so intense that it saturated detectors, overwhelmed initial measurement attempts, and left researchers spending years afterward reconstructing the full picture of what had actually happened. The reconstruction, when it was complete, produced numbers that the human spaceflight community has never entirely set aside. It keeps them in a drawer somewhere accessible for moments exactly like this one. The proton flux during the August 1972 event was so concentrated and so energetic that post-event analysis, using dosimetry models that have been refined and updated multiple times in the decades since, determined that any astronauts present in deep space or on the lunar surface during the event's peak would have received a whole-body radiation dose sufficient to cause acute radiation syndrome. Not elevated cancer risk over a lifetime, not a statistical increase in long-term health concerns, acute radiation syndrome. The kind of dose that produces nausea and vomiting within hours of exposure, causes a measurable drop in white blood cell counts within days, compromises the body's ability to fight infection, and depending on exact exposure duration and the shielding conditions of the environment, carries potential for consequences serious enough that mission survival could not be assumed. More recent estimates, incorporating improved dosimetry models and a better understanding of the event's spectral characteristics, have placed the potential dose for an astronaut in a standard spacesuit on the open lunar surface during the peak of that event at levels that would have been life-threatening without immediate medical intervention that no lunar surface crew in 1972, or today, would have had access to. Those are not speculative projections. They are reconstructed physical estimates based on the actual particle flux measured during the actual event, applied to the actual shielding geometry of the Apollo spacesuit and lunar module. The uncertainty ranges in those estimates are real, and some researchers place the likely dose at the lower end of the life-threatening range while others place it higher. But the central estimate, the number that emerges from the best available dosimetry applied to the best available flux measurements, is not in a range that allows comfortable reassurance. It is in a range that, had astronauts been present, would have defined one of the worst days in the history of human spaceflight. And now here is the specific detail that should fundamentally recalibrate how you think about the Artemis II timing, because this is not just a historical data point, it is the historical data point. The August 1972 solar proton event did not happen while astronauts were in space. It happened between missions. Apollo 16 had returned to Earth in late April of 1972. Apollo 17 did not launch until December of 1972. The most intense solar particle event of the modern space age, the event that defines the upper range of what the Sun can deliver to unshielded human beings in the interplanetary medium, fell in the exact gap between two crewed lunar missions, missing both of them by months, not by design, not because mission planners had identified the risk and scheduled around it, by timing. Coincidental, unremarkable, completely unplanned timing that placed the event in a window when no human beings were in the radiation environment it created. It was, in the most literal and unadorned sense of the phrase, luck. Not precaution, not superior monitoring, not a protective decision made by a well-informed mission management team with good space weather data. Luck. The gap between Apollo 16 and Apollo 17 happened to be there, and the event happened to fall into it, and the astronauts who would have been in its path were safely on Earth, and we have been telling ourselves a story about our readiness for this scenario ever since, without always acknowledging that the first time we truly tested that readiness, the test was passed by absence rather than capability. The mechanics of the 1972 event contain a specific warning that is directly applicable to today. The solar proton event was associated with a series of major solar flares erupting from a single active region that had rotated into an Earth-facing position during August of that year. The proton flux buildup was fast, extraordinarily fast by the standards of solar energetic particle events, which themselves are among the most rapidly developing hazardous phenomena in the space environment. The warning systems available in 1972 were not capable of providing actionable lead time between initial detection of the flare and the onset of dangerous particle flux levels. The particle environment went from background to hazardous in a time frame that, had astronauts been on the lunar surface, would have left them with insufficient time to reach the relative shelter of the lunar module before significant dose accumulation had already begun. The monitoring systems available today are dramatically better than those of 1972. This is not a minor improvement. The Advanced Composition Explorer at the L1 Lagrange point provides continuous real-time measurement of the solar wind and energetic particle environment upstream of Earth. The GOES satellite network measures solar X-ray flux and particle flux in near real time. The global network of ground-based neutron monitors can detect the highest energy components of a solar proton event within minutes of their arrival. The particle event associated with a fast coronal mass ejection today would be detected earlier, characterized faster, and communicated to mission management more completely than anything available to the Apollo program. That improvement is real, and it matters. But here is the question. that improvement does not fully answer, and it is the question that sits at the centre of what we are discussing tonight. The monitoring capability tells us what the particle environment is doing in near real time. What it cannot do, what no current system can do with reliable accuracy, is predict the intensity, duration, and spectral characteristics of a solar energetic particle event before it begins. With enough lead time to change a launch decision or return a crew from deep space before significant exposure has occurred, the warning arrives with the event or shortly before it. The decisions that matter most, whether to launch, whether to delay, whether to modify the trajectory, need to be made before the warning arrives, based on probabilistic assessments of what the particle environment might do, informed by a coronal mass ejection whose trajectory is still unconfirmed and whose shock acceleration potential hasn't been characterized yet. The Orion spacecraft that would carry the Artemis II crew offers meaningfully better radiation protection than the Apollo command module did. The structural shielding is greater. The storm shelter configuration, the specific arrangement of the crew and spacecraft designed to minimize dose during a particle event, has been carefully optimized using the dosimetry data from events including 1972. The mission radiation exposure limits have been set based on current understanding of the health risks, and those limits include margins for elevated solar activity consistent with the current phase of the solar cycle. None of this is nothing. The engineering investment in crew radiation protection for Artemis II is real, substantial, and informed by exactly the kind of historical analysis that the 1972 event made necessary. And yet, the fundamental physics of the problem has not changed. A fast coronal mass ejection, one travelling at 1,872 km per second, as the one currently in transit is, drives a shockwave ahead of it that is among the most efficient particle accelerators in the solar system. The proton energies produced by a strong coronal mass ejection shock can reach levels that penetrate spacecraft shielding that would stop lower energy particles entirely. The dose rate in the Orion storm shelter during a major solar energetic particle event driven by a shock of this speed is not zero. It is reduced, meaningfully reduced compared to an unshielded astronaut in a spacesuit. But reduced is not the same as safe, and the margin between reduced and safe depends entirely on the intensity and duration of an event, whose characteristics are still unknown. We are not in 1972. The monitoring is better, the spacecraft is better, the dosimetry understanding is better. But we are in a structurally similar situation, a fast coronal mass ejection from a solar maximum sun, with an unconfirmed trajectory, approaching a window during which human beings are scheduled to be in the interplanetary radiation environment for the first time in 53 years. The 1972 event missed the Apollo crews by months. The question this event is asking, the question that the space weather data pipeline is currently in the process of answering, is whether the margin this time is measured in months or in hours. In 1972, the gap between Apollo 16 and Apollo 17 was wide enough that the most intense solar particle event of the modern era fell into it without touching anyone. The gap between the current coronal mass ejection arrival estimate and the Artemis II launch window is not measured in months, it is measured in hours. And whether that is wide enough is a question that stereo A data, L1 particle monitors, and a NASA launch decision team are, right now, in the process of answering, with a timeline that is compressing faster than the data pipeline that feeds it. The sun missed in 1972. Whether it is aiming at anything this time is still, as of this moment, unknown. Part 15. The decision pressure. Right now, somewhere inside NASA's mission management structure, a conversation is happening that was not on the agenda when the operational readiness timeline for Artemis II was set. It is the kind of conversation that doesn't show up in press releases or public briefings until after the decision has been made and the rationale has been written up in language that makes the outcome sound inevitable. It is a conversation about probability, about incomplete data, about what level of uncertainty is acceptable when the thing you are uncertain about involves 4 specific human beings travelling beyond the only magnetic protection available to them for 10 days, and it is happening right now, in real time, against a clock that is not waiting for the conversation to finish. The Artemis program did not arrive at this launch window easily. The development history of the Space Launch System, the rocket that will carry the Orion capsule and its crew beyond low Earth orbit, is a chronicle of technical complexity, budget negotiation, schedule revision, and the particular institutional friction that accumulates when a program spans multiple presidential administrations, multiple congressional budget cycles, and multiple shifts in the strategic priorities of the agency running it. The original Artemis timelines, set in the early years of the program, have been revised repeatedly. Each revision added pressure to the next milestone. Artemis 1, the uncrewed test flight that validated the Integrated Space Launch System and Orion system, flew in November of 2022, later than originally planned, but successfully, and with performance data that cleared the path for Artemis 2. The years between Artemis 1 and Artemis 2 have been filled with hardware certification work, crew training, mission planning, international partnership coordination, and the kind of sustained institutional momentum that is genuinely difficult to interrupt once it reaches the weeks before launch phase. The 4 crew members have spent years preparing for this specific mission. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen have accumulated thousands of hours of training in Orion systems, lunar trajectory procedures, emergency response protocols, and the specific operational requirements of a free return lunar trajectory. The ground team supporting the mission, flight controllers, systems engineers, trajectory specialists, communication network operators across the deep space network, have been running simulations and rehearsals for months. The international partnerships embedded in the mission, including the Canadian Space Agency's investment in Jeremy Hansen's seat and the broader international framework of the Artemis Accords, carry their own timeline expectations. None of this creates a safety constraint. Formally, institutionally, explicitly, none of it is supposed to influence the launch decision if the safety case is not made, but it shapes the environment in which the safety case gets evaluated. It determines what counts as sufficient certainty to proceed and what counts as sufficient uncertainty to hold. And it is worth being honest about that, because the history of human spaceflight contains clear examples of what happens when institutional momentum is allowed to quietly reweight the balance between acceptable risk and unacceptable risk. The specific challenge facing the Artemis 2 launch decision right now is not that the risk is clearly unacceptable. If the data showed a confirmed Earth-directed coronal mass ejection with a strong southward BZ and a developing solar energetic particle event already building in the upstream environment, the decision would be straightforward. You hold. The launch commit criteria exist precisely to make that call clear when the evidence is clear. The challenge is that the evidence is not clear. What the data shows right now is a fast coronal mass ejection with an unconfirmed trajectory, an unidentified source, an unknown magnetic orientation, and an estimated arrival window that overlaps with the launch window. The risk is not confirmed. It is possible. And possible but unconfirmed is the precise condition under which institutional pressure is most able to influence interpretation, because there is no definitive data point to anchor the safety argument against the schedule argument. There is only probability, and probability is negotiable in ways that confirmed fact is not. This is the distinction that makes space weather holds fundamentally different from range weather holds, and it is a distinction that is not always well understood outside the operational spaceflight community. A thunderstorm over the Kennedy Space Center launch pad is a binary constraint. It is there or it is not. The Lightning launch commit criteria specify measurable thresholds, storm cell distance, electric field strength, cloud type, that produce clear go or no-go outputs. The forecaster gives a number. The number either clears the constraint or it doesn't. Space weather constraints are probabilistic by nature. The solar energetic particle flux is currently at a certain level, trending in a certain direction, with uncertainty ranges that reflect the limitations of predicting a solar event that is still developing. The coronal mass ejection trajectory has a probability distribution, not a confirmed path. The BZ orientation is unknown and will remain unknown until the event is essentially at Earth's doorstep. Translating that probabilistic picture into a binary launch commit decision requires human judgment operating at the boundary between what the data says and what the decision maker is willing to accept, and that boundary is exactly where institutional pressure lives. What NASA has available today that Apollo-era mission management did not is a real-time monitoring architecture that would have seemed extraordinary to the flight directors of the 1960s and 70s. The Advanced Composition Explorer spacecraft, positioned at the L1 Lagrange point, approximately 1.5 million kilometers sunward of Earth, provides continuous measurement of the solar wind speed, density, and magnetic field orientation, including BZ, as conditions exist upstream of Earth in near real time. The GOES satellite network monitors solar X-ray flux and energetic particle flux continuously, feeding directly into the Space Weather Prediction Center's operational products and into NASA's own mission safety monitoring systems. The stereo A coronagraph provides the angular perspective needed to characterize coronal mass ejection trajectories that Earth-facing instruments cannot resolve definitively. Together, these systems create an information environment where the launch decision can be updated with new data right up to the final minutes of the countdown. A deteriorating particle environment detected by ACE at L1 can trigger a hold call even during terminal count. The system has that capability. What the system cannot do is compress the physical timeline of the information it depends on. The ACE spacecraft at L1 sees the solar wind approximately 30 to 60 minutes before it reaches Earth. At the coronal mass ejection's current speed, closer to 30 minutes than 60. That 30-minute window is real, it is monitored, and it is the most accurate BZUST measurement that current technology can provide with the existing monitoring architecture. But 30 minutes before Earth impact is not 30 minutes before launch readiness commitment. Launch operations for a mission of Artemis II's complexity involve a countdown sequence with constraints and decision points distributed across hours, not minutes. The decision to proceed past certain countdown milestones effectively commits resources and configurations that take significant time and risk to reverse. By the time the ACE measurement at L1 gives a definitive picture of the incoming magnetic field orientation, the launch team may already be past the point in the countdown where a clean hold is straightforward. There is a structural gap here that is worth naming without drama, but without minimization either. The data that would make the Artemis II launch decision unambiguous, confirmed trajectory, characterized magnetic structure, known particle event intensity, becomes available on a timeline that compresses toward or past the decision commitment point. The monitoring architecture is the best that current technology and current orbital infrastructure can provide. It is also insufficient in this specific scenario to provide the certainty that the decision actually requires before the window to use that certainty closes. That is not a criticism of the engineers who built the monitoring systems, or the forecasters running the models, or the flight directors managing the countdown. It is a statement about the current state of humanity's ability to predict the behavior of a star from a distance of 150 million kilometers in real time, with actionable accuracy on timescales relevant to human spaceflight operations. The Apollo program flew its missions during a period when the space weather monitoring architecture was a fraction of what exists today, and it survived, in part because of engineering, in part because of skill, and in part because August of 1972 happened to fall between missions rather than during one. The Artemis program is flying its first crewed mission beyond the magnetosphere, with a monitoring architecture that is genuinely superior to anything Apollo had, and it is doing so on a timeline that is being actively compressed by a fast coronal mass ejection from an unidentified source whose trajectory, magnetic structure, and particle event potential are still, as of this moment, uncharacterized. The launch decision for Artemis II is not just a spaceflight operations question. It is a question about what we have learned from 53 years of working in the space environment, about how we weigh the things we know against the things we don't, and about whether the institutional structures we have built to protect the people we send beyond Earth's protection are strong enough to hold their shape when the schedule pressure and the data uncertainty are both pointing in the same direction at the same time. That conversation is happening right now, and the data it needs to reach a clean conclusion is still in transit, moving toward us at 1,872 kilometers per second, carrying an answer we won't have until we can almost reach out and touch it. Part 16. The overlooked risk. When people talk about solar storms and human space missions, the conversation almost always gravitates toward the same focal point: the astronauts, the radiation, the dramatic, viscerally comprehensible scenario of human beings in harm's way, separated from a lethal radiation environment by a few centimeters of spacecraft hull, and the engineering judgment of people who have never personally experienced what they are designing against. That story is real, it is important, and we have spent considerable time on it for exactly those reasons. But there is a parallel set of risks from this coronal mass ejection that receives almost no attention in standard coverage. that sits below the headline and above routine concern, and that will affect every person on Earth regardless of whether they are watching a rocket launch, tracking a satellite constellation, or simply trying to keep the lights on. And in some ways, it is the more consequential story, because it scales. Start with the infrastructure that the Artemis II mission itself depends on, because this is where the ground-level risk and the mission risk connect in ways that are rarely explained. The Orion spacecraft carries the crew, but the mission doesn't run on the spacecraft alone. It runs on a global network of ground stations, relay satellites, communication pathways, and navigation systems that are distributed across the surface of the Earth and through low Earth orbit, all of them exposed to the same geomagnetic storm environment that a direct coronal mass ejection impact would produce. The spacecraft gets the headlines. The infrastructure is what keeps it connected to the people responsible for bringing it home. The Deep Space Network is the communication backbone for any mission beyond low Earth orbit. It is a system of large dish antennas positioned at 3 sites around the world: Goldstone in California, Madrid in Spain, and Canberra in Australia, chosen specifically so that their geographic distribution provides continuous coverage of the sky as Earth rotates. Together, they maintain communication with every NASA spacecraft operating beyond Earth orbit, from the Voyager probes at the edge of the heliosphere to the James Webb Space Telescope at the L2 Lagrange point to any crewed vehicle on a translunar trajectory. The Deep Space Network is an extraordinary piece of infrastructure, operated continuously and maintained to extraordinary precision standards. It is also sensitive to the ionospheric conditions that a major geomagnetic storm disrupts. The ionosphere sits between the Deep Space Network's dish antennas and the spacecraft they communicate with. For signals travelling to deep space, the ionosphere introduces phase delays, signal dispersion, and amplitude scintillation, rapid fluctuations in signal strength caused by irregularities in the ionospheric plasma. Under normal conditions, these effects are well characterized and corrected, for in the signal processing pipeline. During a major geomagnetic storm, the ionosphere becomes turbulent in ways that current correction models handle poorly. Signal quality degrades, data rates drop. In severe cases, communication links drop out entirely for periods ranging from minutes to hours. For a spacecraft in low Earth orbit, a communication outage of several minutes is manageable. The next ground station pass is minutes away, and the crew can operate autonomously through a brief gap. For a crew on a translunar trajectory, the geometry is fundamentally different. There are no nearby ground station passes. There is one Deep Space Network antenna tracking the spacecraft, and if that link degrades or drops, the crew is operating without ground support for as long as the outage lasts. The timing dependency is what makes this operationally significant rather than merely technically interesting. A translunar trajectory has critical phases, moments when a trajectory correction maneuver must be executed within a specific window to maintain the free return path that keeps the crew safe if the propulsion system fails. Miss the window for a trajectory correction burn, or execute it with incorrect parameters because ground support was unavailable during the planning phase, and the mission's passive safety margin disappears. The free return trajectory, the feature of the Artemis II flight path that allows the crew to return to Earth without additional propulsion if something goes wrong, only works if the trajectory is maintained within specific tolerances. Maintaining those tolerances requires communication with ground teams who are running the navigation calculations and verifying the burn parameters. A storm-induced Deep Space Network outage during a trajectory correction maneuver window is not an inconvenience, it is a mission safety event. GPS-based navigation compounds this picture in ways that extend from the mission directly into the ground infrastructure supporting it. The precision orbital mechanics calculations that feed trajectory planning for the Artemis II mission depend on GPS data feeding into ground-based navigation systems at Johnson Space Center and at the Deep Space Network tracking stations. GPS works by measuring extremely precise timing signals transmitted from a constellation of satellites in medium Earth orbit. The ionosphere introduces variable time delays in those signals, and those delays are normally corrected using models built from empirical data collected during quiet, geomagnetic conditions. During a major geomagnetic storm, the ionospheric delay becomes irregular, spatially variable, and poorly predicted by standard correction models. GPS accuracy degrades, not to zero, but to levels that introduce errors into navigation calculations that would not exist under nominal conditions. For a mission operating at translunar distances where navigation precision is a safety-critical requirement, degraded GPS accuracy in the ground systems feeding the navigation pipeline is a problem that propagates from the ionosphere into the mission trajectory. Now pull back from the mission entirely, because the infrastructure vulnerability that a major geomagnetic storm creates extends far beyond NASA's operational environment. It reaches into the systems that every person on Earth depends on, whether they are paying attention to a rocket launch or not. The mechanism is geomagnetically induced currents, electrical currents driven through conducting structures on the Earth's surface by the rapid variations in the geomagnetic field that a major storm produces. The Earth's magnetic field during a significant geomagnetic storm doesn't just deflect solar plasma from above, it fluctuates, it oscillates, it changes direction and intensity on timescales of minutes. And those fluctuations induce electrical currents in any long conducting structure connected to the ground. Power transmission lines, natural gas and oil pipelines, submarine communication cables, railway signalling systems. The physics is the same as the physics of an electrical generator. A changing magnetic field induces a current in a nearby conductor. The Earth is the conductor. The storm is the changing field. The power grid is the circuit. The event that most clearly defines the modern vulnerability is the geomagnetic storm of March 13, 1989. The storm, driven by a major coronal mass ejection, produced rapid geomagnetic field fluctuations that induced currents in the Hydro-Quebec power transmission network in eastern Canada. The induced currents overwhelmed the network's protective systems. Within 90 seconds of the storm's onset, the entire Hydro-Quebec grid collapsed. 6 million people lost power. The outage lasted 9 hours. Transformers across North America experienced unusual stress. Some were damaged. The United States power grid survived with fewer outages, partly due to different network topology, and partly due to luck in the geographic distribution of the storm's most intense effects. The 1989 storm was powerful, but it was not the most powerful geomagnetic storm the Sun has produced in recorded history. Not even close. The Carrington event of September 1859 holds that distinction. The geomagnetic storm produced by the Carrington coronal mass ejection was so intense that the geomagnetically induced currents in telegraph lines across North America and Europe were sufficient to shock telegraph operators who touched their equipment to operate telegraph systems without battery power from the induced current alone, and in documented cases to set telegraph paper on fire from the electrical arcing at connection points. The global telegraph network, the most extensive long conductor infrastructure of its era, experienced the full impact of a geomagnetic storm that modern instruments estimate would register at DST values, far below anything recorded in the modern instrumental era. If a Carrington-scale event struck today, it would do so against a power grid that is orders of magnitude more extensive, more interconnected, and more dependent on continuous operation than the telegraph networks of 1859. We're not in 1859, we're not in 1989. The power grid has evolved significantly since the Quebec event, and utility operators have implemented some protective measures informed by that experience. The ability to reduce grid interconnection during storm onset, the installation of some geomagnetically induced current blocking devices on critical transformers, the development of space weather alert protocols that give grid operators advance notice of incoming storms. Some utilities are better prepared than others. The preparedness is uneven, and the most vulnerable elements of the grid, the large high-voltage transformers that sit at the core of long-haul transmission infrastructure, remain difficult and expensive to protect fully and catastrophically slow to replace if damaged. A major transformer failure caused by geomagnetically induced current overload is not a weeks-long repair. It is a months-long replacement process for equipment that is custom manufactured, difficult to transport, and produced by a small number of specialized facilities globally. A G4 or G5 geomagnetic storm from a well-aimed fast coronal mass ejection does not need to be a Carrington-scale event to produce cascading infrastructure consequences. It needs to be strong enough, sustained long enough, and geometrically positioned to drive induced currents through the most vulnerable sections of the grid during the hours when protective actions haven't fully been implemented. The 1989 storm met those conditions. The coronal mass ejection currently in transit, if Earth-directed with a sustained southward BZ, has the velocity and the potential energy to meet them again. The astronauts are the story that cameras will follow and headlines will carry. The infrastructure is the story that 300 million people will experience directly if the answer to the trajectory question turns out to be the wrong one. And right now, both stories are running on the same clock, toward the same arrival window, waiting for the same data that hasn't arrived yet. Part 17. The April 4th Alignment. Before we get to the full convergence of factors bearing down on this window, there's one more element sitting in the timeline that I want to mention, not as a cause for alarm, but as one more piece of a picture that keeps getting more layered the closer you look. Comet C/2026. A1 designated MAPS is approaching its perihelion, its closest point to the Sun, in early April of 2026. The timing places its closest solar approach within the same general window as the Artemis II mission and the potential coronal mass ejection arrival. A comet at perihelion, passing through the inner solar system within a relatively close approach distance to the Sun, introduces cometary dust and cometary plasma into the interplanetary environment at a point where the solar wind structure is already disturbed by the coronal mass ejection transit. Comet interactions with solar activity don't produce dramatic observable effects on Earth-scale events in any well-documented way, but in the context of a solar wind environment that is already elevated, already carrying a fast coronal mass ejection through it, and already being monitored for signs of Earth-directed geoeffective activity, the presence of an additional cometary body moving through the same interplanetary medium is one more variable in an environment that is already carrying more variables than it normally would. The space weather environment around early April is not clean. It was not clean before the coronal mass ejection launched. It is less clean now. The comet doesn't change the central question, but it is part of the picture of what the interplanetary environment looks like in the window we're talking about. Part 18. The CIV hypothesis. There's a concept at the edges of solar and plasma physics called critical ionization velocity, a theoretical threshold first proposed by the Swedish plasma physicist Hannes Alfvén, who later won the Nobel Prize in Physics. The hypothesis describes a specific velocity at which a neutral gas, moving through a magnetized plasma, undergoes rapid ionization, crossing a threshold that amplifies the interaction between the gas and the magnetic environment in ways that can accelerate plasma dynamics significantly. The application of critical ionization velocity to solar cometary interactions is speculative. The idea, and I want to be clear that this sits well outside the mainstream of operational space weather science, is that a cometary body moving through the solar corona or the inner heliosphere at the right velocity relative to the solar magnetic field could, in theory, contribute to the triggering or amplification of solar energetic events. It has not been confirmed. It has not been modelled with sufficient rigour to make operational predictions. But it exists as a theoretical framework. It has been applied speculatively to cases where solar activity appeared to correlate with cometary perihelion passages, and in the context of a solar environment that just produced a fast coronal mass ejection from an unidentified source in the same window that a comet is approaching perihelion, it is worth naming as an unresolved question rather than a confirmed mechanism. The Sun is a complex coupled system. The things we don't understand about solar activity are, in terms of sheer volume, considerably larger than the things we do. Introducing that acknowledgement here isn't to suggest the comet caused today's event. It's to note that the framework for ruling it out entirely doesn't exist either, and in a story about uncertainty, that's a relevant data point. Part 19. The stack. Let's put the whole picture on the table at once, because the thing about this event, the thing that makes it genuinely different from a routine solar weather story, isn't any single element. It's the intersection of everything simultaneously. Start with the physical event, an M5 solar flare at 0306 Coordinated Universal Time, producing an R2 to R3 radio blackout across the sunlit hemisphere, associated with a Type 2 radio emission indicating a fast-moving coronal mass ejection shock. That coronal mass ejection is travelling at 1,872 km per second, approximately 4 times the average speed, with an unconfirmed trajectory and an unidentified source region, toward an estimated arrival window of late March 31st to early April 1st. Layer over that the orbital environment, 11,800 active satellites in low Earth orbit, operating at a conjunction frequency of 1 close approach every 22 seconds. with a collision probability of 30% under a 24-hour loss of manoeuvre scenario, down from a 2.8-day safety margin that has shrunk from 121 days in 6 years. That orbital environment has been exposed to 8 straight days of electron flux at elevated levels, continuously stressing the electronics of every satellite in the outer radiation belt exposure zone. Layer over that the human mission, Artemis II, first crewed mission beyond the magnetosphere in 53 years, with a launch window that overlaps the coronal mass ejection arrival estimate, carrying 4 astronauts into the interplanetary radiation environment at a moment when a fast coronal mass ejection, the exact category of event responsible for the most dangerous historical solar particle events, is in transit and uncharacterized. Layer over that the forecast gap. The official pre-event forecast described quiet conditions. The event happened anyway. The trajectory of the coronal mass ejection won't be confirmed for 6 to 12 more hours. The BZ orientation, the single most important physical parameter for determining geomagnetic storm intensity, won't be known until 30 to 60 minutes before arrival. Decision makers across satellite operations, launch management, grid infrastructure, and space agency mission control are working with incomplete information in a narrowing response window. The insight that ties all of this together isn't complicated, but it's important. Systems don't fail at their absolute worst. They fail at intersections. The Starlink satellites in 2022 didn't fail because the storm was catastrophic. They failed because a minor storm intersected with a specific deployment altitude and a specific operational mode that created a vulnerability that wouldn't have existed a day earlier or a day later. The Artemis II risk isn't that space radiation always kills astronauts in deep space. It's that a fast coronal mass ejection with a bad particle event arriving during the specific window when a crew is in the interplanetary medium could exceed the shielding and the forecasting capability simultaneously. The orbital cascade risk isn't that all satellites will fail at once. It's that a correlated, multi-system disruption lasting 24 to 48 hours in an environment already operating at 2.8 days to first statistical collision could be enough to push the probability past the threshold. None of these systems are on the verge of failure in isolation. They are all simultaneously on the verge of failure in combination, and the combination is determined by whether a single, uncharacterized coronal mass ejection, traveling at nearly 2,000 kilometers per second from an unidentified source, is aimed at Earth or not. Timing matters more than magnitude. And right now, the timing of everything is converging on the same window. Part 20. Final question. Let's go back to 0306 Coordinated Universal Time. Half the planet's high-frequency radio communication went silent. Pilots in the air, ships at sea, emergency communication networks, military coordination channels, all of it, simultaneously, absorbed by an iconosphere that had been hit with a pulse of X-ray radiation, travelling at the speed of light from a source approximately 93 million miles away. By the time anyone on the sunlit side of Earth noticed the silence, the pulse had already arrived, already ionized the D layer, and was already dissipating. The warning was 8 minutes, the time it takes light to travel from the sun to Earth, and that warning was invisible, unannounced, and indistinguishable from a normal morning until the radio channels went dead. The coronal mass ejection that followed was not travelling at the speed of light. It was travelling at 1,872 kilometers per second. That's slow enough to give us a transit window, but it's fast enough that the transit window, the gap between launch and impact, is measured in hours rather than days. And within that window, we have a set of unresolved questions that determine whether everything we've discussed is a case study in near misses or something else entirely. Is the coronal mass ejection Earth-directed? The data to answer that with confidence is in the stereo A pipeline. It's coming. If it is Earth-directed, what is the BZ orientation of the magnetic field within the coronal mass ejection body? The answer to that will arrive at the ACE spacecraft at the L1 Lagrange point, approximately 1.5 million kilometers from Earth, somewhere between 30 and 60 minutes before impact. That's the margin. What happens to the Artemis II launch decision? That depends on how the space weather forecast evolves over the next 12 to 18 hours, and on the institutional courage to make a hold decision when the data is still probabilistic rather than definitive. What happens to the orbital environment if the storm is G3 or above, and the disruption window overlaps with the conjunction frequency we've described? That depends on how many operators have already put their satellites into safe mode, how many haven't, and whether the 30% collision probability in a 24-hour window decides to express itself during this particular 24 hours. Here's what I want you to hold when you set this down. The radio blackout at 0306 was real. It was classified. It was documented. The coronal mass ejection is real. It is in transit. The orbital density is real. The 8 days of radiation stress are real. The Artemis II launch window is real. The 1972 near miss is real. The 2.8-day collision clock is real. None of these are projections or theoretical frameworks or speculative futures. They are the current state of the system, confirmed, documented, and ongoing. What is unknown is whether all of them converge on the same outcome, or whether the trajectory resolves to a miss, and the next 48 hours become a rigorous lesson in how close the margins already are without anything actually breaking. But here's the thing about that uncertainty, the thing that keeps resonating the more you sit with it. We are not waiting for something to happen. The event has already happened, the flare fired, the coronal mass ejection launched. The clock is already running. What we're waiting to find out is not whether the gun was fired. We know it was fired. We're waiting to find out whether it was aimed at us. And somewhere in the interplanetary medium, at 1,872 kilometers per second, the answer to that question is already on its way. We just don't know it yet.